Hello, can you hear me? All right, let's start. Okay, so last time we were discussing magnetic forces on a current carrying conductor that is placed inside a magnetic field. So this was a diagrammatic illustration. Suppose you have a magnet, north and south poles. The magnetic field lines will be moving from the north pole to the south pole. So that's the direction of the magnetic field. And this is the current carrying conductor, this line that we see, which I've labeled as with an arrow with I, the current that flows through that conductor. And we saw that how we can use the coordinate axes to figure out what would be the magnetic field's direction, current, and force direction, because it turns out that the magnetic field, the magnetic force, and the current, they're all in perpendicular to each other. They're all normal to each other. And Fleming's left-hand rule is what helps us in determining these quantities such as force, magnetic field, and the current through the conductor. So for example, if I know the current and the force, then I can determine magnetic field. If I know current or magnetic field, I can determine force, and so on. A lot of other possibilities as well. So that's where we left off last time. Today we'll discuss this in more detail. We'll discuss the mathematics, the physics and mathematics of the magnetic force on a current carrying wire or a conductor, right? So I'll just write wire. Okay, so now basically from experiments, magnetism was observed from experiments, and those experiments showed that if I have a wire and that wire carries current, right? And if I put it inside some magnetic field, then from whatever we have studied so far, suppose that this is the magnetic field B, what would happen if I put a wire in the magnetic field? So could you also upload the previous recording? Have I not? If I've not uploaded the previous recording, I'll check and let you know. But I think I have. If I've not, I'll check and I'll upload it. No worries. Okay. So yeah, coming back to this thing, we have a wire that is placed inside a magnetic field. If it is placed inside a magnetic field, there will be a force that is applied to this wire, right? That's what was observed experimentally, and at the time it was not known, and that's how basically magnetism was discovered. This force is a deflecting force because it's deflecting the path of this wire. But the question is, what is the origin of this force? Now we know, we can discuss that because we know that if I have a moving charge, so this wire that I have, it can be also used to show that if this is the electronic charge, this is the path of this electronic charge in the wire in the direction of the current. And if it encounters a magnetic field as well, what happens is it experiences a side wave force, right, which is perpendicular to the direction of motion. Now, a wire that is carrying current, it is made up of not one electron, but a very large number of moving electrons. And so let's try to see what happens inside the wire, right? Now, current in the wire is due to the movement of these electrons. And suppose that if these electrons move towards right, or in any direction, for example, so suppose that they move in this direction, and they move, the electrons are moving, right? So they would carry some velocity. This velocity is what I'll call v drift. Now, what is that? Drift velocity, basically, because the charges are sitting in a magnetic field, they will drift, their path will drift along because of the magnetic force. So with what velocity do they drift? That is known as the drift velocity. Now, from the magnetic field, there will be a magnetic force, right? And the magnitude of the magnetic force that would be exerted, let's call it F. I don't know. Just this is the magnetic force Fm, I guess, or usually I think it's written as Fb. So the magnetic force that would be exerted on this electron can be computed, because it depends on how fast the electron moves, or which is basically the drift velocity. It depends on how strong the magnetic field is, and it depends on the charge of the electron, right? That's why there is magnetic force. So it depends on all of these directly. So the magnetic force is E V. This V is drift again. So I'll write VD and B. Using this expression, we can compute the magnitude of magnetic force exerted on each conduction electron, right? Why each? Because this is just for one electron. If you want the total magnetic force, then you multiply it with the total number of electrons, right? Now, let's draw a scenario. Suppose that this is a plate, and I have an electron. I have multiple electrons here, but let's say that we'll just consider one. Suppose that this distance, the electron is bounded by this distance, and this distance is some value L, right? Suppose that the electron moves in this direction, VD, and the magnetic field is directly out of the paper. So it's coming outside. So we can represent the magnetic field by dots, if you remember, right? So these dots are saying that the magnetic field points in the outwards direction, directly outwards, right? So the direction of magnetic field is known. The direction of the velocity is also known, and there is some force that would be exerted in this direction. We know that because of Fleming's left-hand rule, right? Because the velocity of the electron is basically the direction of the current, right? Because current is moving charges or moving electrons. So the force from Fleming's rule can be shown that it would be in this direction. Now, again, we can, by using Fleming's left-hand rule, we can say that an upward force is applied to the wire, right? Suppose if this electron is just a wire, right? Or one electron inside a long wire. So before I go any further, is there any problem or confusion in this thing? Is the physics of what's happening is clear? That equation, yeah, sure. Okay, so basically, when we perform an experiment in the lab, we see that the force, how strongly is the electron deflected. It would be deflected because of the force. It depends on how fast the electron is moving. The more fast it moves, I'll not write it again. I'll just use this pointer to show it. So how fast it moves, it depends on that. So the more the speed of the electron, the more the magnetic force. Basically, because why do I say that? Because this is the drift velocity. Drift velocity is the velocity that the particle drifts due to magnetic field. Why would it drift due to magnetic field? Because of magnetic force. So the more drift velocity there is, the more drift there is, that means the more force there was initially. And it depends on the magnetic field. The more strong the magnetic field is, then obviously the more stronger the magnetic force would be. This is again how electric field depended on, or the electric force depends on electric field. The gravitational force depends on the gravitational field, and so on, right? So in this case, it depends on the magnetic field in this way. And of course, you multiply it with the charge of the electron, because we are talking about one charge. So this is saying that this charge drifts with velocity Vd in placed inside a magnetic field. So the result of that is equal to Fb. That's the magnetic force that would be produced on that particle. Right. So is that okay? It's the magnetic field. We defined it in the last lecture as well. Let me write it down over here. B is the magnetic field. Vd is the drift velocity. Right? Is the idea of drift velocity also clear to everyone?
Yes, sir.
Okay. Okay, now if you understand the physics of the situation, what's happening, keeping the physics in mind, let's derive the equation for force that acts on a current carrying wire inside a magnetic field. Right now, this is the force that for just one electron, right? So we are not talking about the entire length of wire. Now let's try to understand, if I have a wire of length L, let's go to the next page. Suppose this is a wire that has length L, and 1 second, what happened? And it's placed inside a magnetic field. Okay, so it's immersed in a magnetic field, which is again, let's say it is directed outward. So I'm just going to draw one dot over here, which means that the magnetic field is directly outwards, right? So this is basically the magnetic direction of magnetic field. Remember that it's directly out of the plane or the page. The electrons travel in this length of wire, whatever the length of wire is. Again, I think this representation is a bit weird, but drawing the wire in that direction, pretend that the electrons are moving in this direction, and we'll call this direction the right direction, right? So they're moving to the right, and they move to the right with some drift velocity Vd. And now, if we know the drift velocity, that means we can find out the time it would take to complete one journey along this length L, right? Because any velocity is just defined as displacement over time. In this case, the electron is covering a total displacement of length L, and t is the time. So the time it would take is just the product of the drift velocity times the length of the wire, right? To complete or to traverse the entire journey of length L. right? Now, in that time, in this time, Vd times L, the net charge would be what? It would be Q is equal to I times T, right? That is the equation for the charge. Okay, now I know T is Vd times L. So I can write this as T is, I wrote this down wrong, right? Can you correct it? T is L by Vd. Okay, are you following along?
Yes, sir.
Okay, so it is T is L by Vd. So I'll replace that T in this equation, and this becomes I times L by Vd. So this would be the net charge that would pass in this time T through the end or through the entire length. So now we know how fast is the charge moving, how much time it will cover the entire length, and what is the net charge that would be moving through the entire length of the wire. Now, the magnetic force on this moving charge is, remember, it was Q. Actually, it's Q is just the charge, right? So sometimes let me write it down over here. E is just Q, whatever, because usually we are talking about the charges or electrons that are flowing. So we can replace Q with E. So I'll use Q, which is just E times V, and we have B. Now we only want the component, the perpendicular component, because the magnetic force is perpendicular to velocity and the magnetic field as well. So the perpendicular component is given by sine theta. So I'll multiply sine theta with the magnetic field, right? The only perpendicular part of this would be giving me the force. Now, having this, I can replace Q, which is I L by Vd, and then you have Vd again over here, and then you have B sine theta. Okay, now in this case, the magnetic field, the magnetic field and the force are in perpendicular direction to each other. So theta will be 90 degrees. And this gives me Vd cancels with this. So I get ILB sine of 90. Sine of 90 is just 1. So the magnetic force on this length of wire L is, usually you write it BIL, where again B is the magnetic field, the strength of the magnetic field. I is the current that flows through this wire, and L is just the length of the wire. Okay. Yeah, why is it sine 90? Okay, because it is perpendicular. The magnetic, if you remember from the Fleming's left hand rule, this was the axis that we had. One of them was current. If you go back over here, let me see this one. So this is current, this is magnetic field, and this is force. Force is perpendicular to the magnetic field. So this angle is 90 degrees. So that's why we have sine 90. Is that okay? Oh, basically because the electrons are moving in the right angle to the what do you call this thing? They're moving perpendicular to the direction of the magnetic field, right? The magnetic field, if you look at this thing, sorry, over here, the magnetic field is out of the page, and the electrons are moving perpendicular to that in the right direction. Now the force is exerted by this perpendicular component only. The other component does not contribute to the force, the magnetic force, right? Because the magnetic force is always perpendicular to the direction. So to make the formula correct, we need to include sine 90. So we can just factor out the perpendicular component of that, and which would be affecting or contributing to the force. The other, the horizontal, the cos 90 component, the other direction, any direction, would not be contributing to the magnetic force. It is only the perpendicular part that contributes, because it is in perpendicular to each other, magnetic force and the magnetic field. Right? So this would mean that therefore the force on our current carrying wire, which is inserted in a uniform magnetic field, is just BIL. Right? This is how we can determine that magnetic force. Why didn't we talk about these components in the previous equation then? Oh, you mean in this one, EVD times B, right? Or QVB. Yeah. So basically, in this equation, we're just talking about one electron. We have to, so in general, it is sine 90, right? And sine 90 is what? It is just 1. So in this case, you could include this thing. Let me write it over here. So the formula could be EVDB sine 90. But then this is just 1. So this again reduces to EVDB. But the idea of writing this sine 90 in this part was just to let you know, so that you recall that the magnetic field and the direction of the magnetic field to the direction of the motion of the electrons is always perpendicular to each other. Right? Okay. So let's try to do a problem from this thing. Suppose that you have a power cable, and it has a diameter of say 2.5 centimeter, and this cable carries a current through it. Let's say that the value of that is 2000 amperes. It's a power cable, so it carries a large amount of current, and the distance between the 2 points of the cable, so wherever it is, so maybe it's starting from one house and going to the other one, and let's say that the distance between the two is 50 meters. Right. Now let's calculate, first of all, the magnetic force on the section of the cable between these 2 points, right? So what would be the magnetic force? There would be magnetic force even due to the Earth's magnetic field, right? Now what we can do is, we know that the magnetic force FB is BIL, and then we can you can just write it as BIL, or you can also say that you can include for the sine component and say sine 90, but then that reduces back to BIL. So the magnetic force would be this thing, and the strength of the magnetic field is, oh, I forgot to write that down. The strength of the magnetic field is the Earth's magnetic field, which is around this value, right? So now it's just straightforward. You just put in the values: 30 into 10 raised to power minus 6 into 2000 amperes times we have L as 50 meters. So there, due to the Earth's magnetic field, there would be a magnetic force of 3 newtons exerted on this wire. In what direction would that be? You can suppose that the Earth's the magnetic field is in, suppose if it's in outwards direction out of the page, then you can just use Fleming's left hand rule to find out the direction of the force as well. Secondly, let's compare this with the gravitational force.
Sir, what's D?
Sorry, what's that was the diameter of the wire. Oh, let me write it down. Because the wire will be circular, right? So this is the diameter of the wire. Do we have a unit for magnetic field? Yeah, it's Weber, right? You can find you can write down the unit for magnetic field from this equation. This would be B equals to F over IL. If F is newtons, amperes, and then we have meters. You can even write it down in the base units, but this is defined as Weber. Oh, sorry. Not Weber, my mistake. It's Tesla, right? Did I write it anywhere else as Weber? No. So it's the unit for the magnetic field is defined as Tesla. It's named after Nikola Tesla. The Newton per amperes times meters.
Sir, is it the same as the flux density? Like
the flux density is something else. The flux density, we'll talk about it. It is how much magnetic field lines are passing through a particular area, right? So that's how we define the flux density. And the flux density is measured in Webers, if I'm not wrong. Yeah. Okay, so we're comparing this result, this magnetic force, with the force of gravity. What would be, how strong or how weak is this magnetic force compared to the force of gravity? What would you expect? Should it be weaker or stronger than gravity? I'll give you an example. I don't know if I've mentioned this before, but gravity is extremely weak, right? And it is, we can see that if you have a refrigerator in your home, you have magnets on your, small tiny magnets, or some people like to stick them on their refrigerators. And doesn't matter how small the magnet is, it's very tiny. It sticks to the fridge and it does not fall down. Why is that magnet sticking to the fridge? It's again because of the magnetic force. Now, the entire ball of Earth, the entire sphere of Earth, it's extremely large. All of its gravity is pulling on that magnet downwards. But still, the magnet does not fall, even though the magnet itself is so small. So that even that small amount of magnet can be strongly stuck onto that fridge. And that kind of shows how weak gravity is and how strong electromagnetism is in comparison to that, right? So you would expect the the result of magnetic force or the magnitude of the magnetic force to be much, much greater than the force of gravity. We can figure this out. The force of gravity for this electron in this wire would be just its weight, right? The weight, if I drop it like this vector mg, that's the force of gravity on this thing. Now, how do we compute that? We know that mass is density times volume, right? And volume for this wire, it is a cylindrical wire, so the volume of that is given as pi r square times the length of the wire, right? L. You do the math. This would be pi r. So diameter is 2.5. So the radius would be 2.5 centimeters, so 10 raised to power minus 2 divided by 2 squared, and then you have the length 50. So this gives you about 0.025 meter cube. Right, so that's the volume of the copper wire. We can substitute it back into this equation. The density is about, for copper, the density is about 8,900 kilograms per centimeter per meter cube, and so the volume is 0.025 meters cube. So this gives me about 220 kilograms. And now it's very straightforward to compute the weight. The gravity from, if it's coming from the Earth, then W is just m times g, which is 220 kilograms into 9.81 meters per second squared, which is about 2200 newtons, right? We'll just round it off to that. Clearly, if you want to see the difference of orders of magnitude between the two forces, the force of gravity and the force of the magnetic force, you can take the ratio of these two and see how much stronger the magnetic force is compared to the force of gravity. So this would be 2200 newtons divided by 3.0 newtons, which gives me about, it gives me a large number, but it is 10 raised to power 3 times greater than the magnetic force exerted on the cable. Is that clear? So magnetic flux density is different from B because it has the unit Tesla. Yeah, the magnetic flux